You know, all around us, right this very second, there are these invisible chemical battles being fought. I'm serious. Metals are swapping partners, elements are combining, and it's not just random chaos. It all follows a very specific set of rules. And in this explainer, we're going to uncover them.
I bet you've wondered about this. You get a brand new bike, it's all gleaming and perfect, but you leave it out in the rain and, well, that dreaded reddish-brown rust starts to creep in. So what's actually going on? Because it's not just dirt, right? Nope. It's a full-on chemical transformation.
Well, the answer to our rusty bike mystery lies with one of the most common elements on the entire planet. I mean, you're literally breathing it in right now. I'm talking about oxygen. It's the key ingredient in a process we call oxidation.
Okay, so what is oxidation really? Put simply, it's just when a substance grabs onto oxygen and combines with it. That's it. When something gets oxidized, it has literally gained oxygen atoms. This is our first big building block, so let's lock this one in.
And hey, here's an easy way to remember it. Just think, oxidation is oxygen added. See, the ox in both words is your clue. Simple, I know, but it is super effective. Let's look at a classic example of this in action. When you take a strip of magnesium and it reacts with oxygen, it creates a totally new substance, magnesium oxide. We can describe this with a simple word equation, which basically just shows us what went into the reaction and what came out.
And this is how chemists write it, using symbols to be super precise. It shows us the exact recipe, you know? 2 magnesium atoms combine with 1 oxygen molecule to form 2 units of magnesium oxide. And because the magnesium, the Mg, has gained oxygen, the O, we say the magnesium has been oxidized. Believe it or not, this is the exact same process that happens to the iron on your bike. It's just happening way, way slower.
Okay, so we know what happens when a metal just meets oxygen. But what happens when a metal that's already bonded with something meets a different metal that's just kind of hanging out on its own? Well, this is where the real competition begins.
This is called a displacement reaction, where one metal literally displaces or, pushes out another one from its compound. And a compound is just a substance where different elements are chemically stuck together. But here's the thing. It is not a fair fight. The winner is always the more reactive metal.
The easiest way to picture this is to think of it like a dance. You've got a couple dancing together, that's your chemical compound. Then a more, let's say, reactive dancer comes along and just cuts in. They swap places, and the original partner gets left to dance all alone. It's a chemical cut-in. Let's see how this plays out in a real experiment. Imagine we dip a strip of zinc into this blue solution of copper sulfate. Because zinc is more reactive, it cuts in on the copper, it grabs onto the sulfate, and it kicks the original copper atoms out on their own. And here's the symbol equation. You can see the swap so clearly here. The zinc, Zn, and the copper, Cu, they have literally traded places. Zinc is now buddied up with the sulfate, and poor old copper is left all on its own. Now, all of this begs a pretty huge question. How on earth do we know which metal is more reactive? Are we just supposed to guess? Thankfully, no. Chemists have created the ultimate cheat sheet, a kind of power ranking for metals. And here it is, the reactivity series. This ranking is all about how willing an atom is to react. Metals at the top, like potassium, are super eager, practically jumping at the chance to form a bond. But the ones down at the bottom, like gold, they're much more chill. They just hold on tightly to their own stuff. This list, this is our master key. So the most important part, the one simple rule you need to remember, is this. If a metal is higher up on that list, it has the power to kick out any metal below it. But it never works the other way around. A metal that's lower down can never displace one that's above it. That's the fundamental rule of the game. Okay, so you have the concepts and you have the master key. Now it's your turn to be the chemist. Let's use this knowledge to predict some reactions. All right, let's start with this one. We have some zinc metal and we're mixing it with iron sulfate. Is a swap gonna happen? Think back to that reactivity series. Where does zinc sit on the list compared to iron? Yes, it absolutely will. Zinc is higher on the list than iron, which makes it more reactive. So it easily kicks the iron out, forming zinc sulfate and leaving pure iron behind. See how that rule works?
Okay, round 2. This time, we've got copper, and it's trying to displace magnesium from its sulfate. Remember the list? Where does copper sit compared to magnesium?
And the answer is a definite no. Copper is way down the list, while magnesium is right up near the top. It's just not reactive enough to cut in. So in this case, if you mix them together, absolutely nothing happens.
So now that we've seen these rules in action, let's pull it all together. We've seen how substances gain oxygen and how metals swap places based on a really strict hierarchy. Let's do a quick recap of the key takeaways. So here's your new chemical toolkit. First, oxidation. That's the process of gaining oxygen, like our iron bike rusting. Second, displacement. That's the competitive swap driven by how reactive a metal is. And the golden rule that lets us predict it all comes from the reactivity series. A higher-ranked metal will always displace a lower one.
I'll leave you with one final thought to chew on. Gold is at the very, very bottom of that reactivity list. It's one of the least reactive metals there is. So why do you think that specific chemical property makes it so perfect for things we want to last forever, like jewelry and treasure? It's a great example of how these invisible chemical rules shape the world all around us.